Welcome again to lecture number 14 for the introduction of statistics. I'm your host, Tim. My surrogate host is Tom the T-Bomb. Great little kitty cat, that one. That's our lecture series cat today. It's going to be a long one today. Going to be a very long one. We're going to beat up the t-distribution for inferential statistics, so that means not just confidence intervals, but also the hypothesis testing, and that's for 1 and 2 samples, and then we're going to conclude with the sample size calculations. Now, my apologies for being offline for an entire week, but had to do some adulting, as one does. Especially when there's a gun pointed at your head, so to speak. So that's why we're getting it all done today in one fell swoop. So I guess with that in mind, we should get cracking. Let's go to the next page, because there's a lot of pages. Oh, there are a lot of pages today. So we're going to start off with confidence intervals for a single sample mean. We're going to assume all samples today come from a normal distribution just to keep things nice and compact. Now what do we see on the screen? Well, here's your formula. Let me get my highlighter here. I'm using green today on this one. So this is the formula we want to use. Now, all these formulas for confidence intervals basically follow the same layout. Whether it's proportions or mean values, very little changes. You have your estimate. That is y bar in this case. And then this business here is the margin of error. Remember, in statistics, nothing is exact. We always have to deal with error estimation, and that t star times s over square root n is the margin of error computation for this type of question. T star, this guy, we call the critical value. This is a table lookup. And it will depend on the level of confidence we want to have for our interval. So if we look at the graph off to the right-hand side, you'll see that this is a 95% confidence interval. The only reason you know that is I said so, and it's specific to 35 degrees of freedom. And that's how we get the negative 2.030 and the positive 2.30. Now, just to complete this picture, if there's 95% in the center, then the remaining tails each have to have 2.5%. If you sketch your confidence interval and you can't make it add up to 100%, then you've missed something, which kind of goes without saying, I suppose. Now, like I said, this is on 35 degrees of freedom, so here's how you're going to do this. You can ignore the two-tail probability stuff at the top of this, because what we're really interested in is what's at the bottom of this. So let's go down there. So if at 95%, whoops, a little bit more, there we go. So at 95%, let's try the laser pointer on this one. Are we using green? No, we got the blue one. Okay, so at 95%, no, that's red. I don't want red. Okay, I guess I get red no matter what. Okay, so 95% is right here. Percent confidence. Yeah, we're going to go back to the highlighter, I think. Okay, so here we have 95% confidence. Now, I want to be on row 35. Well, there is row 35. So the intersection of the row and the column is where we get the confidence level. What happened there? There we go, a little better. So that's where the 2.301 came from. Yeah, I don't like that. There we go, that's better. Okay. Now, if you're wondering about that infinity row, recall from a previous discussion that infinity is simply the critical value for the z-based computations. So, because we're not using z, we won't be using that one today. And we will be using t all day, so you're going to get kind of tired of looking at this table, but, yeah, well, that's just the way this whole thing's going to roll out. All right, let's get back over here. What else can we say about this? Well, I think that's about all we really need to say about this. Remember, the goal with these lectures is to keep it simple to get through this course. I know it's the intercession course, so things are happening pretty fast. So this is essentially, here's how to do this, and enough understanding so that you can come out of here saying, yeah, I know what's going on. There's lots of mathematics that hide in the background of all these numbers and all these formulas. We don't need to go there, not today. All right, let's do some examples. That's probably the best way to do this. Oh, one thing I should mention here, I didn't mention it. For single samples, degrees of freedom are always going to be n minus 1 for mean values. So n minus 1. So that would tell me, if the degrees of freedom here is 35, the sample had 36 observations. Moving on to the next slide, we can do some, now this one I left blank in case I needed to do some doodling, so there's no big deal there. So now we have our first example today. Let's move this around a little bit. I want to construct the 95% confidence interval for a single sample mean, where the estimate is 10, the standard deviation is 8, and there are 36 observations. And there's a couple of ads running, so we'll wait for that to play out before we go back on and discuss this methodology. Methodology, is that a word? Yes, it is, but it's probably not the best word. Okay, my water bottle's leaking. Why is that? Oh, well. So while these ads are running, I'm going to try something. I'm going to maneuver something around here previous. Let's do a selection on this table. We'll go control copy on that table. We'll go to the blank page and we'll paste it there so that we can reference it if we need to without any shenanigans. There we go. We got one ad left to go, and then we'll be back talking about how to do this question. And it's just a short ad, too. Thank you, Old Spice. You rock. Okay, let's just see what's going on here. I got some messages coming in, and we'll see what's up with that. You know what? We will deal with those messages in short order, but they're not related to our stream today. So let's just get back to it. Okay. Here we go. Well, the first thing we want to do when we look at something like this is figure out what goes where. So when we talk about an estimate in this course, in this topic, y bar, right here, is 10. There's our estimated value for the mean. The standard deviation of the estimate is 8, so that's S. N is 36. The only thing left to find now is the critical value. So T star will be on n minus 1 degrees of freedom. So we have T star is 35, and that means now I have all this stuff already worked out. Our critical value is 2030. Okay. And that, of course, is coincidental because that's what we have back here on this one. So let's keep on going. All right, so let's plug the numbers in and see what we got. So here we have 10 plus and minus 2.030, and then Our standard deviation is 8, and our square root is that. Now, this is our margin of error. Let's compactify that. That's even a word. So we got 10 plus and minus. So if we multiply this out, this works out to 2.7067. All right, so this is one way to talk about an estimate. It's not an interval yet. We're going to make it so. But if we had to write this up, we could say that from a sample of 36 observations, we had a sample mean of 10, along with a margin of error of 2.7, roughly 2.71, whatever the units are. It could be in kilograms. And we can say we're 95% confident in that estimate. Now, to turn this into a proper interval, what we need to do, I didn't get the right click there, let's try that. So what we have to do for the proper interval then is we're going to have y bar minus the margin of error. Now remember, this is the margin of error. And then we need y bar plus the margin of error. So 10 minus 2.7067 gives us a lower bound of 7.2933 and an upper bound of 12.7067 at 95% confidence. There we go. At its most simple form, that is how to do a one-sample mean confidence interval. We're going to make these a little bit more interesting as we move on, but they don't get terribly complicated. Let's take a look at the next one. Now, what do we have here? Let's move this up a little bit. Now we want to construct a 90%, that out of there. We want to construct a 90% confidence interval for a single sample mean, where the estimate is 2.6. Now remember, that is our y bar. Sample standard deviation is S, that's 1.4. Size is 25, that's our N. And can we conclude that there's a significant difference from the expected mean of 3.0? We're going to repeat this at 80% as well, just to show you a couple of different things. So yes, you can answer hypothesis test questions with this type of thing. The null hypothesis would be that the true value of the mean is 3. And we're asking, is there a significant difference? So the alternative hypothesis would be that the mean is not equal to 3. Okay, let's do that. So there's the formula, same as last time. We have 2.6 plus and minus a critical value, which is a table lookup. So we have sample size 25, that means degrees of freedom are 24. Now let's take a look at that. Now 90% confidence, that's going to be the second column, but I'll verify that by showing you all this. So here's 90%. We'll use the highlighter again. So here we have 90% and 24 degrees of freedom. Okay, my board's acting up. All right, doesn't matter. And that means we're going to have a multiplier of 1.711. I'm not going to use the 4 decimals that the table shows. I'm just going to use the rounded value to 3, because that's what most people will be using. All right, let's go back. So this is going to be 1.711. Now, S is, I didn't move that down enough. There it is. So S is 1.4, and we have to divide out the square root of the sample size, which is 25. Now, 2.6 plus and minus, again, let's get the margin of error. Now, when you work those numbers out, we should get, what should we get on that? Oh, the whole thing. I didn't break it up. Okay. Oh, yes, I did break it up. Okay. Lots of notes today. So this works out to 0.4791. That's our margin of error that we're going to add and subtract to get our, I'm going to move this table out of the way a little bit. I need some room to do a couple of things. Move you over there a little bit. There we go. All right, so we're going to have 2.6, whoops, yeah, we'll do it this way, minus 0.4791 and 2.6 plus 0.4791. This will give us our interval, and this will be at 90%. Now, what does that reduce to? That reduces to 2.1209, and that's the lower bound, of course, and then 3.0791 is the upper bound. So this is the 90% confidence interval. If I redo this, we're going to talk about the hypothesis in a minute, but if I redo this at 80%, then that means the critical value is going to change. So the critical value, T star, for 80% is now 1.318. That's the only thing that changes, and that'll go here. So that's going to give us 2.6, and the new margin of error is 3.69, 0.369, and that turns into a confidence interval, lower bound of 2.2310, and an upper bound of 2.969. Wait a minute. Yeah, no, that's right. Okay. Now, let's see how things have changed. Let's go back up here. The null hypothesis has the mean at 3, and the alternative is that the mean does not equal 3. Well, how do we interpret this? So if we look at the, where's my highlighter here? Let's look at the 90% interval. That's this one here. What do we see? Okay, how come my board is acting weird today? I don't like that. All right, well, what do we notice here? We notice that the hypothesized value of 3 is in here. Mu is equal to 3, and it is inside the interval. Let's get this table out of the way. Whoop. Not the one I wanted this one. Okay, there we go. Now, I can make a note. Here, we fail to find, or we fail to reject the null. And the reason we fail to reject the null is the interval does contain 3. It's inside the interval. However, when we change to the 80% confidence interval, that's down here. We'll use a different color for that one. Here's 80%. We notice at the 80%, if this is on a number line, the H null value, mu is equal to 3, is outside the interval. Our interval here is entirely less than the hypothesized value. So that changes everything. Now we can reject H null, and the reason for that is the interval excludes it. H null, mu equals 3, is outside the interval. And this is going to be how we interpret confidence intervals regardless of the context, whether it's proportions, whether it's one sample or two. If the hypothesized value is inside the interval, you fail to reject. If it's because the idea is that any value within an interval is equally likely or equally valid to be the true value of the unknown parameter. But when that value lies outside the interval, as it does down here in the 80% confidence interval, then we're saying we've excluded it as a possible true value of the parameter. And that's where we get our conclusion from. That's about all I wanted to say about this example, so let's move on to the next one. Now, this one's paired data. Now, a couple comments about paired data before we dive into this question. So, we really can't call paired data independent because in most scenarios, to get paired data, each participant or each subject that's being studied has at least two observations. We could call this multiple comparisons too, I suppose, but we're not going to call it that in this course. So usually this is a before and after scenario. It doesn't have to be that way. Clever wording can change that around. But the point is each participant has two measurements, and the statistics that we're going to analyze comes from the difference between those two measurements. Now, in the interests of doing things, getting a lot of material covered today, I didn't do a complete list of all, well, here's some raw data, let's compute it from scratch. So we're just going to pick it up from here. But usually it's a before and after scenario. So, in the context of medical research, it could be, here's a new drug to lower your blood pressure. So you have 10 volunteers or 20 volunteers. There's another reason why it's not independent. And you establish a baseline blood pressure under certain conditions before you administer the drug. And then when you administer the drug, say over a period of time, then you reproduce the same conditions to re-measure, re-evaluate their new blood pressure. And the difference from the before administration of the medicine minus the values after, in context of that question, well, if there's a non-zero difference that's large enough, it'll be significant. And if it's not, well, it won't be, and that's what we're going to find out. So this corresponds to hypothesis testing. Oftentimes we use mu with a subscript d for differences. So typically the null hypothesis suggests that the mean of those differences is zero, and here we're going to speculate that there is a difference. I'm not forecasting or not predicting ahead of time whether it's greater than or less than here. I'm doing it different from, and that makes it a two-tailed test if this was a hypothesis. The confidence interval, because that naturally addresses. Now, well, this is a before and after scenario, so this is what gives us a big hint that we need to do a paired t-test, or a paired confidence interval in this context. The average of the measured differences is 8, so we're going to call that, just to be different, d bar. Okay, that didn't really show up, so we'll say d bar is 8. Okay. Standard deviation of those differences is 2.36. We'll put a subscript d for that, and there are 10 pairs, so n is equal to 10, not 20. Don't make that mistake. If it was a two-sample test, then it would be different, but because we're working with pairs, there's 10 of them. Okay, you'll notice the formula is exactly the same as the single sample confidence interval, just the notation has changed, nothing else has changed. So let's put some numbers in here and see what we get. Now, we have a difference. A measured difference is 8. We need a critical value for t, and we're on row 8, or pardon me, row 8 for n is 10, so the degrees of freedom will be 9. And we wanted a 99% confidence interval, so that's the far right column. So if we go to row 9, scoot all the way over here, we find that 2.325, I'm going to round that, remember, so we're using what am I saying 2 for? We're going to use 3.250 as our critical number. And then he writes 2 again. I don't know why I got fixating on 2 today. 3.250. The standard deviation was 2.36, and we had 10 pairs, so divide by the square root of 10. Again, there's our margin of error, and let's get a quick computation on that, which I've already done, so I'll keep things moving along here today, because I know this is going to be a long lecture, 19 slides. So yeah, I'm trying to keep it going. So this works out to 2.4255 as our margin of error. Now I need some room to write. Let's move this table out of the way. We don't need that anymore. Zoop. Get that over there. Yeah, I don't know why my board is acting up on this overlay stuff. Regardless, let's not worry about it. So 8 minus that is going to give us a lower bound of 5.5745. And if I add that, I should get 10.4255 at 99% confidence. Now, what about this business here, this assessment? Well, where does 0 lie? Well, if this was on, if we had this on a number line, let's just make some room here. If this was on a number line, 0 would be over here. Mu sub d equals 0 is entirely outside the interval, which means the interval is greater than the hypothesized difference, which would be there isn't one. And this gives us evidence to reject H null. There is evidence from this before and after experiment that there is a significant difference between the data measured before and the data measured after the administration of whatever aspect of the experiment was being executed. And that's that. That's pretty much all there is to that. So those are the 3 types of single sample confidence intervals around mean values. Of course, we have 2 samples to deal with next, and then we'll do all the hypothesis tests as well. Let's scoot on over to that. So here we have, there's a lot to talk about here before we get started. So let's go through this slide. 2 sample mean confidence interval. Again, we're assuming that everything comes from a normal distribution just to make our conversation a little bit more streamlined today. Now, there's the business of pooling versus non-pooling. And pooling, of course, is just the $5 way of saying weighted average versus non-pooled. So when do you know, or how do you know which one to apply? Especially if they don't tell you. If your exam or your instructor says, well, you figure it out, the criteria then is this little formula right here. Take the sample with the largest standard deviation and take that value, divide it by the smaller standard deviation. If it's less than 2, you're going to use pooling. In other words, if the big one is less than twice the size of the little one, you can take the weighted average. And if you do that, you will use this version here of the confidence interval. And yes, that's a monster to compute, so be careful with your calculator. If you're not using pooling, you can use this one. Now, the trade-off, and I'll do both today, is degrees of freedom. Degrees of freedom for pooled is pretty simple. It's in sum of the 2 sample sizes minus 2. The compact way for non-pooling is take the smallest of the 2 samples and subtract 1. But there's a more complicated formula for figuring out the degrees of freedom using this formula, using this version for the pooled or non-pooled standard deviation. And that is V1 plus V2 squared divided by V1 squared over N1 minus 1. Then we have v2 squared over n2 minus 1. Yeah, that's a pain, but most software does it this way, and it will give you a different answer. And that is where either the VI's is equal to S, the variance, divided by your prof is going to show you or expect you to do. I'm going to show you how to do both for non-pooled examples today. And I need the practice anyway. I haven't done it this way for a while. But yeah, that's the trade-off. I'm not entirely sure which is the best way when it comes to lazy man statistics. It's like, well, I don't know if I do non-pooled, the square root's easier, but then if I got to do this, that's a lot of work. But then there's pooled, and you got that, and that's a lot of work. So I don't know which one is actually better. Guess it comes down to pick your poison. Okay, well, we've got examples ready to go. Let's take a look at those. We're going to do a 99% confidence interval to compare the two sample means, keeping it very simple. Here's the numbers. For sample 1 has a mean of 8, standard deviation is 4, sample size is 20. For sample number 2, the mean is 6, the standard deviation is 6, and the sample size is 30. So let's check and see, do we use pooled or not? Pooled. Okay, so the large sample standard deviation is 6, and the small is 4, and this is clearly less than 2, so we use pooled, which of course you probably already figured out because I've already included the formula over here, but that's fine. You will get the other one shortly. So let's do this. Now, I like to have positive numbers, so we're going to go sample 1 minus sample 2, so we don't have to chase negatives around. It's just a complication, so we don't do that. Let's not do it that way. We already have the formula sitting there. I don't need to rewrite it again. So here we're going to have 8 minus 6. So this is the estimated difference. Now the critical value. Well, if the degrees of freedom are the sum of the two sample sizes minus 2, then we have to use 48 degrees of freedom. But of course, 48 degrees of freedom is not on the table, so we have to round it down. Never round up. And I believe the table I have is 45 degrees of freedom. Let's just verify that by bumping our way back to our, where did I put that? I do have it, I think it's on this one. Nope, not that one. Not that one. I did put it somewhere. Ah, that's the one I want. Let's take a look at that. Okay. Boom, 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 boom. Why, no, I don't have 45 degrees of freedom. So on my table, I have a 40 degree of freedom, and I would pick one of these numbers through here. Let's use that pointer again. So mine doesn't have 45 degrees of freedom, although I am going to use 45 degrees of freedom. Did I use 45 on here? Let me just check. Two samples, 2014. Yeah, I got that off my calculator. Okay, that's fine. But we're going to use 45 degrees of freedom. If your table doesn't have a 45, then you'll pick one of these, probably the 20211. But that's just what you have to do when you're dealing with this stuff. Whoops, there we go. Now, or 40 DFs. This is dependent on what your table has. So for us, we're going to use the 45, and that is 2.014. That's the critical number. Now, we have two square roots we have to construct. So sample 1 minus 1 is 19, multiplied by the variance. Remember, variance is standard deviation squared, so I'm just going to write it that way, 4 squared. And then over here, we have 29 times 6 squared. And remember, when I do square roots, I put a little hook at the end, just say the square root ends here. So this is going to be 20 plus 30 minus 2. So this is where we got the, that's not right. Boom, boom, boom. 48 degrees of freedom. And then we need 1 over 20 and 1 over 30. So this is called the pooled standard deviations, pooled standard error. Let's compactify this into something kind of more useful. So this is 2 plus and minus. Now I've pre-calculated everything, as long as I can read my handwriting. So if you're trying to work this out and you are not handy with a calculator, I did itemize these two square roots because I know you'll probably want to try and get it right, which would be good. Now this works out to 2.994 for the first square root. The next square root is 0.2887. There we go. So let's turn this, and specifically when I say this, let's turn this margin of error into one number. So here's 2 plus and minus 3.0813. 3.0813. So that gets us to there. Now let's turn this into an interval at 99%. Now, oh, we got an ad. I'm going to take a moment to double check a couple of things. Bump back a little bit. 99% at 40. Yeah, I don't like that. I think I screwed up. That's, yeah. Yep. I knew it. Rats. Okay, we're going to recompute that. Do 99%. I grabbed the wrong number. Now, I'll grab the calculator to grab that. Menu 556. 99% confidence is 0.005 in a tail. And we had 45 degrees of freedom. So that should have been 2.6896. And of course that changes that. So 2.6896 times 5.2994 times 0.02887. Whoa. That's, I screwed that up. Extra 0 in there. That's better. We back yet? Oh, yes. So while those ads were running, I took a second look at that critical number and realized I made a major mistake on that. So I fixed it. So you'll notice here, let's put this in red, this has changed to a correct value, and I'm just recomputing the margin of error now, which is 4.1149. There we go. Now, we can turn that into a lower bound, upper bound statement. So the lower bound will be 2 minus that last answer, and that's going to be negative 2.1149, and the upper bound will be 6.1149. There we go, at 99% confidence. I must have, well, I'm not entirely sure what I did there, but I got the wrong critical value, but now it's fixed up. Now remember, the question with this one was, let's get this back over here, 99% confidence interval to compare two sample means. Now if we talk about this in context of hypothesis testing, the null hypothesis is mu1 minus mu2 is 0, because if two things are the same and you subtract them, you should get 0. The alternative hypothesis here will be mu1 minus mu2. We'll just use it does not equal 0. Well, look at this. We have an interval that spans 0. We have a negative value for the lower bound, a positive value for the upper bound. So not only is the measured difference in here, where we have y bar 1 minus y bar 2 is equal to 2, but also in this interval is mu1 minus mu2 is equal to 0. So there's really no difference between the measured values and the expected differences. And this means we can fail. Our conclusion is to fail to reject H null in context of hypothesis testing. Or we could summarize by saying that we have a measured difference of 2 units, along with a margin of error of 4.1 units, the lower bound of negative 2.1 and an upper bound of 6.1 at 99% confidence. It's certainly plausible that the true value of the different mean values is 0. And that's how we do that. Okay, let's move on to the next one, because this one's got some computations. Apparently I also can't type either. Let's fix that up. Is there, get that W out of there, okay. Is there a significant difference between the samples described below? Here we have sample mean 1, sample mean 2, but we have to determine whether it's pooled or not. I mean, you can see over here we're going to do the non-pooling anyway, but how you would check that is you would go 8 divided by 3. Remember, that's from this stuff here, right? 8 divided by 3 is greater than 2, and greater than or equal to 2, so this will be the non-pooled version. That's what we want to do. Okay, let's do this the quick and easy way first. Oh, I didn't specify a confidence level. Well, let's use 90%. Okay. Actually, let's see, what did I use when I worked out the answer to this? I used, I did 99%. No, that's the wrong one. Oh, there's where my mistake happened. How silly. Yeah, I kind of pooched that. My bad. That previous one should have been at 95%, but that's fine. We're going to do this one at 99% as well. I misread that. Sorry about that, but that's why we do it live. 99% here. And now, if we use the compact version for getting our critical number, smallest n minus 1, well, here we have n, the small one, is 26, so degrees of freedom will be 25. And on 25 degrees of freedom, at 99% confidence, we get the critical value of 2.787. And let's just verify that by going back to that table. Okay, so on row 25, that's here, and 99% confidence, we have 2.7874. We're only going to use the 3 decimals today. So this one is correct. Cool. I wonder if that's caused by my highlighter. Let's see, do that. Highlighter didn't stick. Let's try the laser pointer. Sometimes I think it's the laser pointer that messes this up. However, yeah, still broke. Doesn't matter anyway. All right, let's go back to our question. We know we got the right setup. Let's put some numbers in. Okay, the difference in the two means is 1. I mean, this is 11, this is 10. I'm not even going to write that down. The difference is 1. And now we need a critical number, which we have, 2.787. And now we need the square root for the standard error. So S1 squared, that'll be 8 squared over 26. And then we're going to have 3 squared over 36. Now, how did this work out? I'm wondering if I should just recompute that. No, I got this one right. So 9 over 36, 64 over 26. That's right. Okay, so here we have 1 plus n minus. Let's turn this whole thing in. Well, we'll do the square root separately. If you want to check your work against it, that's fine. My square root worked out to, oh, right, I did pooch this one earlier too, didn't I? Yep. Okay, that's what we have a calculator for. Let's just quickly do that. So here we have 64 divided by 26 plus 9 divided by 36. Now that's under the square root. That'll be 1.64. And then he writes a 6. Okay. 1.6467. And we'll multiply that by our 2.787 to get a margin of error 1 plus and minus 4.5893. Well, that one's going to span 0, I think. That's pretty obvious. So this then is a lower bound of negative 3.5893. Looks like it. 5893, and an upper bound of 5.5893. So is there a difference? No, because we span 0. Spanning 0 means no difference. So we fail to reject the null hypothesis again. Or we could summarize by saying that the true value, with 99% confidence, the true value of the difference lies between negative 3.6 and positive 5.6. Now, this was done with 25 degrees of freedom. We're going to do the alternative calculation now. And let's move this around so we have some room to work. All right, we'll have to move it again, but first thing we're going to do is we're going to work out what the V values are. So V1, that was this, 64 over 26. I'm going to write that as a decimal. And then we have V sub 2, which is 9 over 36. Well, that's just a quarter, so we'll simplify that. So this is just 0.25. 64 over 26, however, is an annoying little decimal of 2.46. Good enough for me. We're just going to run 2 decimals. I don't want to chase 4 decimals around with all this. All right, there we go. Now, n here is 26, and n here was 36, because we're going to need those. Got to go do n minus 1s, right? And let's do that formula. You'll see this is the long, tedious way, but sometimes you got to do it that way. Degrees of freedom, the hard way. The degrees of freedom then will be V1 plus V2 all squared, V1 squared over N1 minus 1, and V2 squared over N2 minus 1. So, what is V1? Well, that's 2.46. This one was 0.25. We'll square that. Now down here we're going to have V1 squared. That's 2.46 squared over 25. And this is going to be 0.25 squared over 35. Let's simplify the numerators and denominators now. 2.46 plus 0.25 gives us that, and if we square it, we get 7.3441. Now let's get that first denominator. 2.46 squared divided by 25. So this will be 0.2421. And then we're going to have 0.25 squared divided by 35, which will be ridiculously small, 0.0018. Now, almost done. 7.3441. What's that bottom stuff add up to? 0.0018. Again, that's quite rounded too, by the way. Plus 0.2421. And we get 2439. It's a decimal, 0.2439, by the way. So if we simplify that, at 7.3441 divided by last answer, and we get 30.1111 degrees of freedom. Now, of course, you can't have a partial degree of freedom, so you round down. You never want to claim more information than you're entitled to. So we get 30 degrees of freedom the hard way. So these two methods will very rarely ever match up. And sometimes they can be quite far apart. Here, the difference isn't too much. Okay, let's move on. Let's move on to hypothesis testing. Now, we're going to start with single sample means. Again, we're going to assume that all the means come from a normal distribution, and that basically simplifies down to one formula for now. Yeah, when we get to the two sample stuff, we'll be back to pooled, non-pooled, but there's nothing we can do about that. Degrees of freedom then will be n minus 1. That's pretty much all there is to say on this. I was going to doodle some other things on this particular slide, but I think we'll leave that. The doodling will come when we do the problems. And just as a note, when we do the pooled versus non-pooled, I will do the difficult computation for degrees of freedom as well. Let's look at our first question. Given the following information, test whether the sample mean is significantly greater than 8. We'll use a 5% level of significance. And the sample mean is 11. Sample standard deviation is 3, n is 40. And we're going to do the critical value method as well as the back. Copy this back to our previous slide and talk about that for a moment. We'll paste it in over here. Boom, there we go. Now, that's why we have in the numerator these guys, 2 tail probability and 1 tail probability. This is where alpha is going to show up. Okay? So for 1 tail critical values, we just use alpha. If it's 2 tail, it'll be alpha divided by 2. So this is for critical value discussion. Let's say we have 1 tail. Alpha is 5%. Degrees of freedom will be 20. What is the critical value? Oops, put that in the wrong spot. What is the critical value? And that's what I use the asterisk on T for. Well, let's take a look at 20, row 20. And 95%. What am I saying 95% for? 5%. So this is one tail probability. So that means we're looking at this. Well, here is the one tail probability. Alpha is 5%. We're on row 20. So this test statistic, or pardon me, the test critical number is 1.725. 1.725. So critical numbers work opposite, or interpreted in an opposite manner from p-values. The larger the test statistic, oh, that's a terrible bell curve. Let's just get the hat out of there. Okay, let's try this again. Okay. Okay. Annoying. Come on. I want a... Wow, this is really breaking today. Okay, what's going on? I seem to be froze. I don't appreciate that. Okay, well, maybe it's busy thinking about something. I see my hard drive is busy spinning. Oh, there we go. Now let's get rid of that. Let's try again. This time eraser. All right. Let's see if we can get through here before the computer says, I've had enough of you. Let's make a bell curve, just a nice little bell curve. Now, when we were talking about p-values, okay, why are you being a pain? Okay, when we were talking about p-values, the rejection region is always out here in the tail. This is where you reject, H null. Because the further you are from center, significance increases. So significance increases as t star, or calculated t, increase. Remember, p-values get smaller when that happens. So the point I'm getting at is, for me to reject at the 5% level of significance using critical values, the corresponding test statistic is 1.725. I will reject the null hypothesis if my obtained test statistic t is greater than or equal to this value. So that's reverse from how we do p-values. In p-values, you're less than or equal to. But for critical values, you are greater than or equal to. Just remember that significance increases as the critical number or the test statistic increase as well, because you're further and further away from center. That's the idea. Remember, significance is all about how different your calculated value is from the expected value. So it only makes sense that the bigger the difference, the less likely it occurred due to random sampling variability. In other words, type 1 error. All right, with that in mind, let's go over here. So what's the critical number for this? Well, let's find out. So t crit on this. So over here we have sample n is 40, which means 39 degrees of freedom. Now that is not available on a, oh, wait a minute now, how come, why am I, oh, there's a problem. I have to recompute this one right from scratch. Okay, because on my written notes here, I made a mistake. Let's make this a little bit easier. Let's say this is 41. So sample is 41 instead of 40. So that means degrees of freedom will be 40. And I know that is on the table I have displayed here. Now, let's get the critical number. And I'm using 5% level. It's a one-tail test. That means we're using this column, the second column. And row 40 will be down at the bottom here. We're going to use 1.684. 1.684. So that means if my test statistic, when I calculate t using that formula, is greater than or equal to this, then I have a rejection at the 5% level of significance. So let's do the math. What do we get? So y bar was 11. We were expecting 8. Standard deviation was 3, and the sample size was 40. Now my written notes are no good because I used an incorrect value. So what do we get? The top is 3, obviously, and then we need 3 divided by square root 40, and that is 0.4743. So our test statistic, let's move that table out of the way a little bit. Okay, that's not moving the table. Yeah. There we go. So 3 divided by that gives us 6.325. Good enough. Well, that's a very large test statistic. So doing the critical value method, we see that t, sometimes this is referred to as t obtained, so we can say that t obtained of 6.325 is greater than the critical number, which was 1.684, so we reject H null. Boom. That's how you do that. If we do the p-value method, then we have to look at the table. Now we're looking at row 40 for 40 degrees of freedom, and that means I need to move this around again. We have to ask, where does that value fall? Well, let's look down here for a moment. Here's row 40, and we follow this all the way over here to the right. We can see that our test statistic isn't actually on the table. It's on the right margin of the table. Look, it didn't blank out that time. Cool. All right. Now, what does that mean in terms of p-values? Well, let's look up here. In terms of a one-tail probability, we can say that the p-value is smaller than that. And the reason why is the test statistic, our test statistic is out here. That means the p-value has to be smaller than either this or this, if it's a one-tail or a two-tail hypothesis test. Well, it's a one-tail, so we have this. So the p-value method says that p-value is less than 0.005. The conclusion remains the same. We reject H null. There we go. Let's carry on. Let's go back over here. Now, another one sample test. Single sample mean is 19.75. We want to know, is this significantly smaller than the expected mean of 20? We're going to use both assessment methods at the 10% level of significance. S is equal to 2, N is equal to 30. So what are the hypotheses? Well, let's write them down. H null says the mean is 20. The alternative hypothesis, as given, is less than 20. And alpha is 10%. That means we need a critical value that corresponds to that. Now, degrees of freedom will be 29. That's n minus 1. So let's find out the critical value. Now, let's see here. I wanted 10%, and it's a one-tail, so we're going to use this column. Oh, now it's acting up again. What a weird machine. Okay, well, it's not the machine's fault. It's the computer software. All right, so on row 29, we have 1.3114. So we use 1.311. Is that what I used on my notes? Yes, it is. Okay. But you'll notice it's a less than, so we want that to be negative. So this is going to be negative 1.311. And if we think about that for a minute, let's just move this around a little bit more so I can see the table. Remember, it's the further you get out from the center. So if you're heading this way, which is your less than direction, of course you're going to act up again. So bell curve, quick and dirty bell curve. So not only does significance increase as you go this way, significance increases as we go this way as well. So that's why we're using negative 1.311, and anything further out, in other words, more negative, will be a rejection of the null hypothesis. Now it's time for some numbers. So t is 19.75 minus, I think it was 20. Yes, it was, right there. Now, what was our standard deviation? It was 2 and n was 30. So in the numerator we have negative 0.25, and the standard error on this particular question is, where did I write you down? I didn't break it out. I just left out the final answer. So we'll put it in. Not a big deal. So we have a calculator. Divided by 30. Square root 30 is 0.3651. Oh, we got an add. Okay, well, we'll just get this down here first. And then we'll wait for the add to run out. 6847. Okay. Ooh, it skipped the dishes one. Cool. There's only the 3 adds. The second one's almost done, and then we'll be on again. And we're back. Okay, so I've just been doodling while this was running. So simplifying the math, we get an obtained test statistic t is negative 0.6847, which of course is not significant. You can see that if we go back up here to what I was doodling while we were on the break. Remember, this is our critical value. Our obtained value is this. And this is the rejection region. Unfortunately, this is the fail to reject region. Whoop. So if this is the fail to reject region, our p-value must be very large. We can check that too, by the way. So if we look on the t-table, which is actually right here, we can see it on the bottom. We have 29 degrees of freedom right there. Our test statistic being, now this is where we ignore the negative sign, but we have 0. I can't write on there. So 0.6847 is smaller than this value, which means our p-value then must be greater than this value. So either way we do this, we end up with the same conclusion, that we fail to reject the null. Let's summarize that. So t, obtained t is, no, that's the wrong direction, try that again, is less than t crit, or the p-value is greater than the level of significance. In both cases, we fail to reject H null. P-value, by the way, if you're wondering, is whatever the heck it is. I didn't work it out with the calculator, but the p-value is definitely greater than 10%. And by quite a bit, I would suggest, given the size or the lack thereof of our test statistic. Moving on, he said. And we got another paired example. So just like we talked about with the confidence intervals, paired data comes from a usual before and after scenario. Hypothesis for this will usually be that the mu of the differences, in other words, what were you expecting them to be? Well, 0. And the alternative will be whatever the question states. And we want to assess this for a difference from 0. So this will be mu sub d is not equal to 0. So if alpha is at 10%, now with a two-tail test, you're either going to double the p-value or, using critical numbers, we'll divide alpha in 2, and we get 0.05, and then we want a critical value for that. Now degrees of freedom for this will be 8, and let's just go over here, if I got it all written down. Critical value is 2.306. Okay, there we go. Let's, I bumped the button on my stylus. It kind of did wonky things. Okay, and this will be plus or minus because this is a does not equals. We're not prejudging whether greater than 0, which would be positive 2.306, or less than 0, negative 2.306. All that remains to do now is calculate the test statistic and make a conclusion. Let's do that. Now here we have t. Now d bar is negative 1.5. Standard deviation is 2, and the sample was 9 observations. We had negative 1.5, and this is 2 divided by 3. So this should be negative 2.25, because the math on that one is easy. Now, how does that compare to our critical value? Well, it doesn't. Well, it does, but it's less than. So we see that t is less than t star. In other words, negative 2.25. Now, wait a darn minute. Now, this is where we got to be careful here, okay? When you move to the left in negative land, this changes. That's why I don't like doing it this way. Oftentimes for folks that are less than comfortable with negative numbers, this gets kind of messy. But the point is, this isn't as, our obtained t isn't as negative as the critical t. So note the negative sign. That's why this is kind of confusing. This is where the p-value method really comes out ahead. So this is a fail in this case. Fail to reject. Now, what about the p-value? Because when we do the p-value method, we don't care about the signs. We don't. Now we just need to look at that table again. So we had a test statistic, and we're comparing to 5, let's just get the p-value, and let's see what we get. There we go. Let's move this around a little bit. Okay, so remember it's two-tail probability. So that means I'm using 10%. 10% two-tail probability. If I was to divide it by 2, I'd get this. We had 9, was it 9? 8. 8 degrees of freedom. And our test statistic was 2.25. So our test statistic lies between 2.306 and 1.85, which means our test statistic produces a p-value less than 10% and greater than 5%. Let's go back over here. So this is if you're going to get tripped up on something, it'd be one like this. So just be careful with this. So we can say the p-value is less than this, but greater than this from the table. So what does that mean to us? Well, it means we get to reject the null. Wait a minute. Did I get that right? No. Alpha divided by 2, we fail to reject the null. Sorry, my bad. Getting all tangled up in my own numbers. Anyway, we're failing to reject the null hypothesis because if we just took the one-tail probability, which is bigger than 5 and less than 10, and doubled it, we would have something bigger than 10. And, of course, this was the original level of significance. Okay, so watch out for that. It's easy to get that messed up. Let's move into the two-sample, because time, well, actually, no, we're not too bad. We'll get this done in 2 hours, I think. All right. Come on. I'll move that up there a little bit. Okay, so for two-sample means, we have the same scenario again as last time. We're either going to be doing pooled or non-pooled. And that depends on this right there. Oh, now you're not going to... These slides are weird. Pardon me. We will use pooling as before if the large standard deviation divided by the small standard deviation is less than 2. If it's greater than or equal to, we will use the non-pooled version. Pooled is this very annoyingly large and complicated formula. The non-pooled is this much nicer formula, but of course it comes with more complicated degrees of freedom if we do it the hard way. We will also, we will do it the hard way as well, just to show it again. And we're also going to do the critical value method as well. Moving on, let's get some questions out of the way here. So at the 1% level of significance, is there evidence that sample mean 1 is greater than sample mean 2? And of course there's our numbers that we're going to work with. Let's write out the hypotheses. So H null has 1 minus 2, mu 1 minus mu 2 is equal to 0. The alternative hypothesis is that mu 1 minus mu 2 is greater than 0. Now 1% suggests that alpha is that, and the critical number that goes along with that, let's just flip over here to my notes so we don't have to mess around too much. So you'll notice that the total, so this is going to be a pooled test, and the reason why it's pooled, where am I going to write that? I'll write it up here. We're using pooling because, that's supposed to be an S, not a 2. Okay, so this is going to be 2.5 divided by 1.5 is less than 2. Now, what's our critical number? This is on 100 degrees of freedom, by the way, because, let's use our highlighter on this one. Here we have degrees of freedom, and now you're not going to work again. So the degrees of freedom are the sum of the two sample sizes minus 2. So this is on DF 100. And that's on almost every table. So if we look that up, we should get 2.626. And we have the table here. Let's go ahead and check that. And if we look at the bottom, row 100, there is 2.626, just what we want. Cool. Now, let's write this out. So t on 100 degrees of freedom. And we're using this formula here for pooled t. Measured difference is going to be 2.5 minus 1.5. There's our numerator. And we have 2 square roots to deal with in the denominator. So n minus 1 for the first sample is 50. And then we're going to multiply by the variance, which is 2.5 squared. That'll be 6.25, but you can check that on your calculator. Then we have 50 again, and 1.5 squared. Well, that'll be 2.25. And we're going to have 51 plus 51 minus 2. So this is where we got our 100 degrees of freedom from. Now, let's get this other little rascal in this. Be 1 over 51 and 1 over 51. So that's simple. That's just 2 over 51 if you want to pop that in your calculator in a more efficient manner. But you do you. I'm not your real dad. Now, what do we have here? So the difference, the measured difference on this thing in the numerator. Did I write something down right? Oh, I did the wrong number in there. I'm getting number blind. Means we're 2 and 2.5. This should be 2. Okay, so that's the measured difference is 0.50. And the 2 square roots, when we simplify them, so the first one is 2.0616, and the second square root is 0.1980. So if we do all that, we end up with a test statistic of 1.2247. So that is our obtained t. How does that compare to the critical t? Well, it's clearly less than, so this is a fail to reject. And the conclusion then is we fail to reject H null. In other words, 1.2247 is less than the critical t, which I said was 2.626. Now, what's the p-value for this? Large. We are on row 100. Oh, back over here again. So row 100, where does 1.2247 land? Well, 1.2247 is just so very slightly off over here in the left-hand margin. So if it's in the left-hand margin, that means the p-value is going to be here as well, which means we're greater than 10%. P-value is greater than 10%, and again, the conclusion remains the same. We're done with that. Okay, we got one more example left to do, and then we're going to do a couple of examples about computing sample size, and then we're going to be done with this topic. Again, if you're joining late, my apologies for being off Twitch for the last couple of days. Had to do adulting things and just didn't have any, that was a combination of lack of time and mental horsepower is being expended on other things. Okay, at the 2% level of significance, is there evidence that the sample mean for sample 2 is greater than sample mean number 1? Okay, let's find out. Now, how are we going to do this? Well, let's start off by writing out the hypotheses. So H null, as always, is mu1 minus mu2 is equal to 0. Now, the alternative is mu1 minus mu2 is something else. Now, I'm saying 2 is greater than mu1, or y bars in the other way. So this is going to be negative, because if the second sample value is greater than the first sample value, and we're subtracting, it's going to have to be a negative value. And if alpha is equal to 2%, we need a critical value then at that point. And that'll come from our friendly neighborhood table over here. So, one-tail probability, you know what, I'm going to change this because the 2% level of significance is, I don't want to have to compute something with my calculator. That's what I'm getting at. So to make our life a little easier, let's look at that. Let's change this. That'll be the way to fix this up. Different from. Okay, let's learn how to type. There we go. There we go. Done, done. That changes this, of course, to a does not equal sign. And that means we have to divide alpha by 2. Let's do that. Alpha divided by 2 is 0, 1, and we're going to get a critical number now. Okay, so two-tail probability here, and degrees of freedom. Now, the smaller the two sample size methods have 20 minus 1 to get 19 degrees of freedom. Now, let's look over here. 19 degrees of freedom. And one-tail probability means we need 2.5. Oh, that's going to round. Whoops, hang on now. 19 degrees of freedom. So we're going to use this one, 2.540, for the critical number. Now, let's write that down. Come on. Okay, I didn't want to do that. I wanted this. 2.540. Now we can do the math. I will compute the other degrees of freedom here momentarily. So here we have t. Now, we want to go 7 minus 9, and then we're down here. Now, sample 1 had, again, another typo. This will be 2 squared over 20, and then we're going to have 5 squared over 30. Much simpler this way. Now remember, this is a non-pooled test because this. Non-pooled because s equals 5 divided by s is equal to 2 is greater than or equal to 2, so non-pooling. Boom. All right, t is equal to negative 2. What's the denominator on that? 10165. And that means this works out, when we divide that out, it's negative 1.9674. So this is t obtained. Now, this is another situation where we are in the fail to reject conclusion result. Let me illustrate this perhaps a better way than I did last time. Okay, but I cannot draw a horizontal line today to save my life. Okay, good enough. Now, to reject, I need to be out here in the tail, the reject region, and that begins at the t critical value of negative 2.540. It's negative because I'm on the left-hand side of the curve. But our obtained value here negative 1.9674 is in the fail region. It's not quite how you spell region, but now it is. Okay, so this is the fail region, and that's where we unfortunately landed. This is all about the failure to reject the null hypothesis here. The reject region would have been out here, and we're not there. So that's an easier way to understand this, I hope. Okay, what's the p-value? Well, the p-value must be large if that's the case. We calculated negative 1.96, and we did that on 19 degrees of freedom. And that puts us down here, looking over here at this table now. Let's just check and see something here. So 19 degrees of freedom, and our test statistic was 1.96. So it lands between these two columns. So we had to go up here. Now if this was one-tail probability, it would be smaller than 5%, but bigger than 2.5%. But this is two-tailed probability, so we're less than 10 and greater than 5. But I have alpha at 2%, and therefore we fail to reject, because our p-value is greater than the level of significance. Now, so our p-value, a little bit of room to write, our p-value was less than 10%, greater than 5%, but alpha was at 2%. So again, fail to reject. And there we go. Now, let's do the promised degree of freedom computations. So what do we have here? We had 2 and 5. I just want to double check this. So here, let's do this. Zoom. And we'll copy that. And we'll move down here. And we'll paste it somewhere. Oh, it didn't paste. Okay, well, whatever. It's here somewhere. All right, so the formula we're using again is V1 plus V2 all squared. Then we need V1 squared over N1 minus 1. Then we need V2 squared over N2 minus 2, where each of these V values is equal to the variance over the sample size. Now, what was our variance? Well, for sample 1, we had, so for S1, we had 2 over 20. So let's do it this way. So this works out to 4 over 20, and that is 0.20 last time I looked. And then we have, for the second one, we have 5 over 30. So this will be 25 over 30, which will be 0.8, unless I miss my guess. Yeah, that should be right. No, that's not right. Well, it's close, but it's not quite right. Where's my calculator? Let's do that. 25 divided by 30 should be 5 over 6, which would be about 0.84, I would think. Let's move this out of the way. 25 divided by 30, 0.833. We're not going to chase that any harder than that. Yeah, there we go. Okay, so let's do this thing now. Degrees of freedom. V1 is 0.2, V2, 0.8333. We'll square that. And then we'll divide out. So here we have 0.20, we'll square it, n minus 1, so this is 19. Over here we got 0.8333 squared, and we'll divide this by 29. Zoom. Let's come down here. Okay, so let's figure that top part out. And what do we get? We get, so the numerator is 1.06 and a whole bunch of 7s, so we'll round it to that. Now let's do the denominator. 0.2 squared divided by 19 is a small number, 0.0021. And then we have 0.8333 squared divided by 29, and we get 0.0239. And keeping on, what does this work out to finally? We have 1.0678 divided by denominator. We get 40.6 degrees of freedom. Well, that's not anywhere near the 50 we had before, so this rounds to 40 degrees of freedom. So the difference here was about 10 degrees of freedom, and that's pretty typical for this technique. Anyway, we only have one more topic left to talk about, and we can wrap this long-winded speech up. How to do sample size computations. Oh, hey, we got a break. Okay, we'll do that. Make a couple of notes on the screen while we're waiting for that to clear. Can I write on there? Oh, it'll stay too. Look at that. Right on. Okay, so just a couple of notes. When the ads are done, we'll talk about this, do an example for each, and we'll call it a day. And this ad's almost done, and then we'll get back to it. Okie doke, there we are. We're back. Okay, so there's two formulas in this course for calculating sample sizes. They're both very much the same. The thing that doesn't change between the two of them is this. We need a critical number from Z. Typically, we're going to find that from the bottom of the T table. We can get it off the Z table too. You know how to do that by now. The only thing that's really different then is for proportions, we're going to multiply by P star and 1 minus P star. So P star defaults to 50% unless you're told otherwise. And if we're doing the sample size for mean values, then we use a given value for variance. And oftentimes they'll give that in terms of standard deviation, so just remember to square it. M is the desired margin of error. If it's in proportions, it is. All right, let's do an example of this. So let's do proportion example first here. So let me move this around a little bit. Okay, so let's say we want n for proportions where the margin of error is 2% at 95% confidence. Am I going to make that fit? Nah, we'll just do it here. Okay, so if I'm going to do that, I'm going to use the first of those formulas up there. So 95% confidence, just a table lookup. We should know it by now, is 1.96. Margin of error 2% is going to be written as 0.02. Now, we're going to square that. Now, I didn't give a value for proportions, so we're going to use p star default to 0.5. So this will be 0.5 times 0.5. And the thing with using 50% for p star is this will give you the largest possible sample size. Any other combination of p stars that add to 1 will give a smaller value. I'll demonstrate that in a moment. So let's work this out. Grab the calculator. So first off, we have 1.96 divided by 0.02. That's 98. And if I square that, that's a ridiculously large number. So this will be 9604, and this is 0.25. So the sample size in this situation then is 2401. Now, that is with the default p star. Now let's compare. Let's say that we know from historical studies, or we have information that let's let p star equal 0.45. Well, now we're going to have n is equal to the same thing before, 1.96 over 0.02, square that, but now we're going to have 0.45 times 0.55. So again, this is going to be 9604, but now we have something different. 0.45 times 0.55 is 0.2475, and that will give us a smaller sample size. That'll give us 2376.99. Now, here's the thing to remember. Regardless of the decimal, whether it's large or small, you round up. 2377 is the recommended sample size. It's always better to have one extra than one too few. So for this, we always round up, never down. And that's how you do that for proportions. Now let's just pop a new page, and we'll do one for mean values. So this is going to be z star over the margin of error squared, and then we need variance. So now let's say we want calculate n for 90% confidence with a margin of error of, let's say we're working with kilograms, just for giggles, 0.5 kilograms, and sigma is equal to 1.5. Okay, straightforward. N, now the critical number, again it's a table lookup, so for 90% is 1.645. We have a margin of error of 0.5. We're going to square that, and then we need sigma squared, so this will be 1.5 squared. Let's work this out. 1.645 divided by 0.5 basically doubles that to 3.29, and we square that, we get 10.8241, and 1.5 squared is 2.25. So to complete the calculation, we get 24.35. But always round up. So we have to have a sample size of 25. There we go. There's really no more complications to this question or this type of question. They all work out about the same. And that is the conclusion. I told you it was going to be a tour de force today, and that was a good 2 hours. That had to have been at least 2 hours. So I thank you for putting up with that. And again, I apologize for not being on Twitch streaming for this past week, but adulting things took precedence. That's why we try to cram it all in today. I know this is a complicated topic. There's lots of little things to know. But there it is. Review the stream as needed, and I wish you the best of luck for this stuff. We still have 2 more topics to talk about. We have analysis of variance to talk about. I'm just going to write that down. Still to come is ANOVA. Okay, yeah, this is running out. And regression, simple linear regression plus correlation. So that's all that remains to talk about. And ANOVA will just do that by itself. Correlation and simple linear regression will do that by itself. And then it'll be exam time. I'll try to throw together some exam review stuff too. Anyway, I've been talking for 2 hours. You've been listening for 2 hours. I think that's time to call it a day. Why don't you folks go have yourself a great day. Best of luck with your studies. And we'll talk again sooner than later. Okay, bye-bye.